In this video, we are going to go over exponential equations, part 1. Specifically, our goals in this video are to understand exponential equations, to solve exponential equations using the base exponent property, and to solve exponential equations using common logarithms, or we could even use the natural logarithm as well. So first of all, exponential equations. So these are equations that have variables in the exponent. So our goal, just like with any equation, is to solve for the variable, which is another way of saying find the value of the variable that makes the equation true. So one property that we'll talk about is the base exponent property. So first, let's take a look at this example. We have 2 to the power of x equals 8. If we're solving this, the value of x is the value that makes the equation true. Another way to think of it is 2 to what power equals 8, and that would be 3, because 2 to the third equals 8. Okay, but there's another way that we could solve this problem as well, and that's by, if possible, we can write, the left-hand side is already written. With an exponent, we have 2 to the power of x, but if we can write the right-hand side with the same base of 2 to the exponent, we can equate the exponents together. So 2 to the x, 8, another way of thinking of 8 is 2 to the power of 3. So now these have the same bases, and if they have the same bases, it means their exponents must be equal. And so that's the property you see below, that if we have a to the x equals a to the y, notice our bases are the same, that means that x has to be equal to y. Or if our bases are exactly the same, the exponents have to be equal to each other. Okay, so let's do some examples. So example 1, solve for x. So we have 2 to the x is equal to 16. Using the base exponent property, or another way of saying, let's make sure that they have the same bases. So 2 to the x stays as 2 to the x. 16 is 2 to the fourth. Okay, so now since the bases are the same, the exponents are equal. This means that x is equal to 4. So now let's check it. And in order to check it, we take the value that we got for x, substitute it into the original equation, and determine if it's true. So we want to know if 2 to the fourth is equal to 16. Well, 2 to the fourth, you can do this in your calculator and multiply it out. We get 16 equals 16, which means that x equals 4 is the correct answer. Okay, next solve for x. So we have 4 to the 2x is equal to 64. Let's see if we can get these to be same bases. So 4 to the 2x would stay as 4 to the 2x. 64 is 4 to the third. So when you're doing this, notice how there's a base of 4 on the left. You want to see if 64 can be written as base 4. If it can't, we'll talk about that in the next section that we do. But when you're looking to use the base exponent property, you're looking to see if you can get the bases to be the same. Okay, so now that we have the same bases, we can set the exponents equal. 2x equals 3, and we solve this like we would a linear equation, where we divide 2 on both sides to get x equals 3 halves. It's perfectly okay to get a fraction. So let's check it. So we have 4 to the 2, and then x is 3 halves, and we want to know if that's equal to 64. Okay, so in our exponent, the 2's cancel, and we're left with 4 to the third equals 64. 4 to the third, you can do that in your calculator, but we would get 64 is equal to 64, which means we found the value that makes the equation true. Just be careful, don't put 64 as your final answer. The value we got for x is 3 halves. Next, solve for x. So we have 3 to the power of 5x minus 3 is equal to 81. Since we have a base of 3 on the left, we want to see if we can write 81 with an exponent with the base being 3. So 3 times 3 is 9. 3 times 3 times 3 is 27. 3 times 3 times 3 times 3 is 81. So 81 is 3 to the fourth, because 1, 2, 3, 4. And then we had 3 to the 5x minus 3. So since our bases are the same, we can set the exponents equal to each other. So we have 5x minus 3 is equal to 4, and we solve this like we would any other linear equation. So we have 5x equals 7, divide both sides by 5 to get x equals 7 over 5. Okay, so that would be our final answer. Next, example 4, solve for x. So we have 3 to the power of x squared minus 4 equals 1 over 27. So you might know that 27 can be written with a base of power to 3, but this is a fraction. So recall negative exponents. 3 to the negative first is 1 over 3 to the first, which is 1/3. 3 to the negative second is 1 over 3 squared, which is 1 over 9. 3 to the negative third is 1 over 3 cubed, which is 27. So 27 is 3 to the negative third power, and it's okay to have negatives in our powers. Okay, so we have 3, this is x squared minus 4x is equal to 3 to the negative third. With our bases the same, we set our exponents equal to each other. So we have x squared minus 4x minus equals negative 3. And we have a quadratic equation. We have x squared. So now we'll use the strategies that we talked about to solve quadratic equations by getting everything over to one side and having it set equal to 0. And then we can use factoring, square root property, quadratic formula, any one of the tools we've learned. Okay. So we add 3 to both sides. We get x squared minus 4x plus 3 equals 0. This can factor. We can find two numbers that multiply to 3 and add to negative 4. So we have x minus 1 times x minus 3 is equal to 0. So we would get x is equal to 1 and x is equal to 3. So both of these would work in this case. Okay, so next we're going to talk about the logarithmic property of equality. For example, if we have log base 7 of x equals log base 7 of 49, if our logs have the same bases, the expressions inside have to be the same. So this would give us x is equal to 49 in this case. Okay, so the property down below, also before I do that, this also means that, let's say, okay, so the property down below, we have log base a of m, so m would be the expression, equals log base a of n. That means that the expressions inside have to be equal to each other. And this arrow should be going both directions, because the other thing that we're allowed to do is if we have m is equal to n, we're also allowed to take the log of whatever base we want of both sides. And that can help us to solve exponential equations, as we'll see in the next section. So if the bases are exactly the same of the log, then the expressions inside of the log must be equal. Okay, so recall properties of logarithms. We have the change of base formula. We have the product rule, where if two things are being multiplied inside, we can rewrite that as addition. We have the power rule, where if there's a power, it comes out as multiplication. And we have the quotient rule, which goes into subtraction. Okay, so what we're going to do is we're going to be able to use these properties to solve exponential equations when we can't get the bases to be the same. So really there's two ways to solve exponential equations. One is we make sure that the bases are the same and we equate the exponent, and two is what we're going to talk about next. Okay, so solve for x, express irrational solutions in exact form and as a decimal rounded to 3 decimal places. So we have 7 to the x is equal to 8. So we can't get these to be the same base. So what we can do instead is we can take the log of both sides. Now you can take the log base of whatever you want, but you want to be a little bit strategic here. You want to maybe use the common logs, because we're going to use a calculator, which also means that you could use ln. Okay, you could also take, since 7 is being raised to the exponent, you could take log base 7 of both sides as well. So I'll show you a couple different ways to do this. So first I'm just going to take the common log, or log base 10 of both sides. So I get log 7x is equal to log 8. Using properties of logarithms, this x can come in front to give me x log 7 is equal to log 8. And now remember, log 7 is just some number. So this is some number being multiplied by x. So to get x by itself, we divide log 7 on both sides. Okay, so x is log 8 divided by log 7, and I'll do this in the calculator in just a minute. The other way I mentioned doing this is if we have log, let me rewrite the original problem. So 7 to the x is equal to 8. Remember that log base a of a is equal to 1. So notice here that 7 is what's being raised to the exponent, so you could take log base 7 of both sides. Base 7. So we have log base 7 of 7 to the power of x equals log base 7 of 8. Okay, using properties of logs, this exponent can come down in front. We have x is log base 7 of 7 equals log base 7 of 8. And then log base 7 of 7 is just equal to 1 by that property I mentioned. So this gives us x equals log base 7 of 8. but we still have to do change of base formula in order to find the answer for this. And I believe the software would also be looking for this as a final answer. Okay, so no matter which way you go, we end up at the same spot. To get the decimal, you put it in your calculator, you just use the log button. Log 8, close the parenthesis, log 7, close the parenthesis, and we get, let me erase this just a little bit, we get 1.06862 ... and this is asking us to round to 3 decimal places. So we go 1, 2, 3. So we're rounding the 8. We look next door. Since the number next to it is greater than, is 5 or bigger, we have 1.069. Okay, and that's 1, 2, 3 decimal places. Next, we have solve for x, express irrational solutions in exact form, and as a decimal rounded to 3 decimal places. So we have 8 to the power of negative x is equal to 2.7. So we have 8 as our base on the left, and we can't make 2.7 as a base with an exponent as the same base as 8. Okay, so this is where we would use the logarithm property and take the log of both sides. Just to show you, you can also take the ln of both sides, but the reason you want to use common log or ln is that's what your calculator can do. Your calculator can't do any other bases of logs, which is why we have the change of base formula. Okay, so for this one, just by way of example, you can use the common log. I'm going to do the ln of both sides. So I have ln of 8 to the negative x is equal to ln of 2.7. In order to solve for x right now, it's up there in the exponent, but by using the power rule, I can bring it in front. Now to solve for x, we divide by negative ln of 8. Okay, so even though the negative is on the outside, we're still going to divide by negative, so we just get x by itself. So this gives us x is equal to negative ln of 2.7 over ln of 8. So this is our irrational solution in exact form. And then you would plug it into the calculator. So you would plug in negative ln of 2.7 divided by ln of 8, and we get negative 0.477653, and we're asked to round to 3 decimal places. So we go to the third, so the third spot after the decimal, look next door. Since that number is 5 or greater, the 7 goes up to 8. So our exact form to 3 decimals is negative 0.478. Thank you for watching. If you have any questions, please feel free to reach out to me.